This lesson is about complex arithmetic. Complex, not because it's difficult, but because it involves complex numbers. So let's take a look at what we're talking about with complex numbers. If you recall, I is the square root of -1. And a complex number looks like a plus bi. And that's where a is the real part and b is the imaginary part. So we're going to be talking about adding these numbers, subtracting, multiplying, or dividing. And we'll also talk about something called a conjugate. So first let's just add some complex numbers. Let's take u, which is 2 plus 4i. W is 9 minus 6i. And let's just add u plus v, or u plus w, and see what happens. So I'm going to take 2 plus 4i and add 9 minus 6i. And let's see what we get. We just add like terms, like you used to do in Algebra 1. We're going to add the 2 and the 9 and get 11. We're going to add the 4i, subtract 6i, and get minus 2i. So our result is 11 minus 2i. Is it possible for us to add two complex numbers and get a real number? Well, sure. If we happen to add two numbers where the complex part disappears, it cancels out, we're just going to get a real number. For example, if I wanted to add -3 plus 4i plus 7 minus 4i, you'll see again if we add like terms, -3 and 7 would be 4. If I add 4i and then I subtract 4i, I get no i's. No i's. So I just get 4. Now this type of thing is going to happen really often if I have these creatures called complex conjugates. Complex conjugates occur when I'm using the quadratic formula. Because if you remember in the quadratic formula, you start with -b plus n minus the square root of b squared minus 4ac all over 2a. So that plus and minus part is where the conjugate comes from. So if I have something like a plus bi, the conjugate would be a minus bi. Similarly, if I were asking for the conjugate of a minus bi, it would be a plus bi. The notation for a conjugate is a bar over top. So the conjugate of a plus bi is what that bar over a plus bi means. And that would be a minus bi. For example, if I had 6 minus 3i, and I want to find the conjugate of it, I just changed the sign of the imaginary part. So 3i, the -3i would become plus 3i. So the conjugate just changes the sign, S-I-G-N, of the imaginary part. If I were to add two complex conjugates, for example, if I add 6 plus 3i and then 6 minus 3i, obviously I'm just going to get 12 with no imaginary part. Okay, so in general, a plus bi plus its conjugate, a minus bi, is just going to give me 2a. And again, no i's. All right, quick property. If I have z plus w and I'm trying to take the conjugate of that sum, it's just the sum of the conjugates. So no big surprise there. You can take your conjugates first, then add them together, or you can add them together and then take the conjugate. So no difference in the order there. Now for multiplication, if I want to multiply a scalar times a complex number, I just do what you did back in high school. Algebra 1 said you just distribute the 2 to both terms. And so I'm going to get negative 6 plus 10i. If I wanted to multiply two complex numbers, for example, 4 minus 5i times negative 2 plus 3i. Now you may have called it in Algebra 1 FOIL. It was just the distributive property. You can call it FOIL, Leoff, Philo. It doesn't really matter. Distributive property. It's all the same. You just want to make sure every term here gets multiplied by every term there. So if I do the first, I get negative 8. If I do the outer, I get plus 12i. If I do the inner, I get plus 10i. And if I do the last, I get minus 15i times I, right? Which is I squared. Now what is I times I? Okay, recall. I was square root of negative 1. So I squared would be negative 1. Okay, so that's going to turn this into negative 8 plus 22i plus 15. And so you can see finally that the answer to this is going to be 7 plus 22i. Okay, so no big surprise there. Note that if you do complex conjugates, a plus bi times a minus bi, what's going to happen when we do the outer term and the inner term? Well, if I do the first term, I get a squared. The outer term would be minus abi, but the inner term is plus abi. So those are going to cancel out. But then I'll get minus b squared I. Substituting that I squared is negative 1, I then just get a squared plus b squared. We're going to use that fact when we divide, because we don't like seeing a complex number in the denominator. So you can see I need to divide 3 minus 2i by negative 1 plus I. So for division, what we do is we multiply by the complex conjugate of the denominator. So negative 1 minus I. And remember, from good old Algebra 1 again, if you want to multiply, the only thing you can do that's not going to change the form is multiply by 1. So I want to cleverly disguise the 1 in a way that's going to be useful to me. So I'm multiplying top and bottom by the complex conjugate of the denominator. On top, I get using FOIL or philo or Leoff or whatever, it doesn't matter. Negative 3, outer gives me minus 3i, inner gives me plus 2i, and last gives me plus 2i squared. In the denominator, now you can just use this fact we have up here if you want, or we can go ahead and work it out. First gives me positive 1, outer gives me plus I, inner gives me minus I, and last gives me minus I squared. Okay, combining terms up here and using the fact that I squared is negative 1, we're going to get negative 3 minus I minus 2 on top. And then this just becomes 1 plus 1 in the denominator, which we can then say is negative 5 minus I over 2. Or you can even write that as a complex part and a real part of negative 5 halves minus 1/2 I. Okay, so division's not that bad. You just have to remember to multiply by the complex conjugate of the denominator. So we've covered addition. We can do subtraction if we can do addition, because subtraction is just adding a negative. We've done multiplication. We've done division. One last thing I wanted to touch on is order of operations. So just a quick example for order of operations. If I'm trying to do a conjugate and then I have another conjugate somewhere that I'm trying to do later, we have to remember that that bar has implied parentheses. For example, if I'm trying to do u, which is 2 plus 4i, w, which is 9 minus 6i, and I want to work out u, w, but the w is a conjugate, and then I want to take the conjugate of the whole thing. I want to do it in order of, remember how you used to do in Algebra 1? You did inner parentheses first? Okay, I pretend like there are parentheses around this w bar. So I'm going to do that conjugate first, then I'm going to work out the multiplication, then I'm going to do the conjugate of the whole thing. Okay, so if I had 2 plus 4i, I'm going to carry along that big conjugate there. I'm going to go ahead and fill in the conjugate of w, 9 plus 6i. I'm going to work out the multiplication, then take the conjugate. So I'm just going to keep carrying along this big bar. 2 times 9, 18. Outer was 12i, inner 36i, and last plus 24i squared. So let's continue working on the inside first, and then we'll apply the conjugate. Got the conjugate of 18 plus 48i, and then remember I squared, negative 1. So 24 times I squared would be negative 24, or minus 24. 18 minus 24 is negative 6. So I have negative 6 plus 48i. But that's inside of that big, long conjugate bar. So now I apply the conjugate. So last but not least, I get that that's negative 6 minus 48i. So we've covered everything that I can think of for complex arithmetic.